to give people a little time to move in here for the next session, about another minute or two. Okay, so as to stay on time, we'll go ahead and start the next session. We'll start with an invited talk by Ophelia Tsui from Boston University. And the title is Liquid Crystal Alignment by Optical Interference and Applications to Liquid Crystal Diffraction Gratings.
Thank you, Chairman. I would like to thank the organizers for having me in this workshop, and it is really an honor for me to be asked to give the talk here. The main subject of this talk is about making inhomogeneous surface patterns. Can everybody hear me?
There.
Yeah, right. Thank you. The main subject of this talk is about making inhomogeneous surface patterns for alignment of liquid crystal. In the following 30-some minutes, I will explain how inhomogeneous patterns like those you see in the background and at the bottom align liquid crystal and why it is interesting. And then I will detail how we use optical interference method to make these surface patterns. And finally, I will demonstrate how we use these surface patterns to make liquid crystal diffraction gratings, which form some important elements in some optical projection systems. Now, to bring out the motivation, I need to briefly review the working principle of LCD. And for illustration, I will use that of the 90-degree twist nematic liquid crystal cell. Shown in this cartoon is the arrangement of the nematic liquid crystal molecules inside such a cell, in which you can see that the rod-like molecules undergo a 90-degree twist along the vertical dimension of the cell. Now, light comes in from the top and is linearly polarized parallel to the liquid crystal director at the top plate. Now, the optics of this device is such that the light polarization will rotate with the twist of the molecules. And therefore, in the end here, the light polarization will be rotated by 90 degrees. And at the exit, there is a second polarizer with its optical axis rotated at 90 degrees to the first polarizer. And with this arrangement, light can pass through the device. Now, suppose now we apply an electric field across the cell such that it aligns most of the liquid crystal molecule vertical. And with that, when light passes through the cell, there will be little change in its polarization, and so it will be blocked by the second polarizer. So this shows how one can use electrical signal to easily control the on and the off state of the LCD device. But importantly, it demonstrates that it is important to be able to control the liquid crystal alignment at these boundaries. In the example that we just discussed, we can see that it is important that we can anchor the liquid crystal at the boundaries to support this 90-degree twist. Therefore, it is necessary for us to be able to control the liquid crystal alignment. So in general, there are two angles to control. As many speakers of this workshop have pointed out, there are two angles. So one is the azimuthal alignment angle phi, and that determines the twist of the liquid crystal molecule inside the cell. The second angle is the surface critical angle theta. It also has important effect on the operation of some LCD devices. Now, at the time when we started the project, there was no reliable technology for achieving values of theta in the 20 degrees to 45 degree range. On the other hand, there are potentially better LCD designs that do require required the values of theta to be in this range. And that motivated us to figure out a way of doing it. Now, our approach involves the so-called frustrated boundary, which basically is composed of an array of multiple liquid crystal alignment domains. Now, shown in the bottom is the topographical image of the multiple alignment domains patterns that we fabricated by using atomic force microscopic local oxidation. Now, in these patterns, the alimentary domains are made of parallel grooves, either in the x direction or in the y direction. The way these patterns work is the following. Because pneumatic liquid crystal possess macroscopic orientational ordering, so they tend to align with the local grooves. However, with the grooves alternating between the x and the y direction, the liquid crystal would have to adopt a configuration like those you see here, which are wiggling. However, the wigglings correspond to deformation in the liquid crystal directed field, and that leads to elastic energy. Imagine now you decrease the pattern period, that elastic energy is going to increase. And at some point, the energy will be so large that the liquid crystal would rather relax into a uniform configuration, which by symmetry of this pattern should be along the 45-degree azimuthal alignment. But this is not the end of the story, because now the liquid crystal is at 45 degrees, which is misaligned with the local groove direction everywhere. And that increases the surface energy between the liquid crystal and the surface. And if that surface energy is large enough, the liquid crystal would rather tilt out of the plane in order to reduce that energy. Now, we have confirmed such physical picture of the liquid crystal alignment on these pattern surfaces that we fabricate by the AFM, and I'm going to show you the data. Now, shown in the top series are optical images of the liquid crystal cells, where the bottom cell is made of the AFM pattern surfaces that I just showed you in the previous slide, and the top plate is made of ideal glass with polyimide that is uniformly routed along the y direction. And these cells were obtained between cross polarizers. So essentially, you can use the optics that we discussed earlier for the 90-degree twist pneumatic liquid crystal cell to understand these images. Okay, from here you can see that as we systematically decrease the pattern period P, the checkerboard pattern homogenizes. Now, in particular, when the pattern period is equal to 0.8 micron or less, we find the cell look completely uniform. By measuring reflection spectrum, we deduced that the liquid crystal tilt angle on these two cells are the same and has a rather large angle of 40 degrees. We have confirmed this observation by computer simulations of the liquid crystal configurations on these checkerboard patterns based on energy minimization. So these results, both simulation and experiment, show that we can indeed use the frustrated boundaries to achieve large liquid crystal reticle angle. However, there is a serious drawback with this method, and that is the AFM method that we use to make these patterns can only make patterns that are 25 micron by 25 micron in size, which obviously is too small for practical applications. That motivated us to pursue the photo-alignment method that I'm going to describe. The material that we use for this method is an azo dye with molecular structure like that you see here, and it has the nickname of SD1. Previous experiment shows that this material absorbs UV light with an absorption peak at 327 nanometer. Now, importantly, it was observed that when this material is illuminated by linearly polarized UV light, the long axis of the molecule rotates perpendicular to the UV polarization. And in turn, the photo-aligned azo-dye material aligns liquid crystal along the long axis of the molecules. So our idea is to use photo patterning of this material to produce multiple alignment domain pattern like that you see here, where the arrows indicate the preferred alignment direction of the azo-dye molecules. We use the setup shown here to do the patterning. The light source that we use is helium cadmium laser with wavelength of 325 nanometer, very close to the absorption peak. Lenses 1 and 2 expands the beam to 5 millimeter diameter. The expanded beam first passes through a first halfway plate before it gets split equally into two beams. The first split beam passes through the second halfway plate, and the second split beam is reflected by a mirror, which brings it back to coincidence with the first beam, where they interfere to produce an interference pattern at where we put the azo-dye film. To produce the pattern that we want, we actually need to carry out the patterning in two steps. In the first step, we rotate the optical axis of this first halfway plate to 45 degrees. Now, because the inlay polarization direction of the UV laser is along the y direction, so this will rotate the UV polarization to X. And the second halfway plate simply adds a phase to the first split beam to a quantity equal to this exponent, where NO is the ordinary refractive index of the halfway plate, D is the thickness, and lambda is the laser wavelength. The significance of this phase will become apparent later. So then we allow the azo-dye film to be exposed to the resultant interference pattern for some time before we turn off the laser. And with this, the exposure should lead to parallel domains inside the azo-dye film, where the azo-dye molecule should be alternatively aligned in the y direction because the UV polarization is along X, and in other domains where there should be little azo-dye alignment. Now in the second step, we rotate the optical axis of the first halfway plate to vertical, and that returns the UV polarization to the y direction. And with that, when the first split beam passes through the second halfway plate, it acquires a phase given by this exponent. Now, because this is a halfway plate, and therefore the difference between this phase and the phase that we acquire in the first step should be exactly pi. And with that, the interference pattern that is produced now should be shifted laterally by a half pattern period with respect to that we acquired in the first step. And therefore, exposure to such interference pattern would complete the multi-domain alignment structure that we want. Showing here are the optical images of liquid crystal cells that are made of the photo-aligned azo-dye films I just discussed. So as you can see in here, that the quality of the pattern is rather high and over a large area for a wide range of pattern periods from 1.6 micron to 10 microns. Now, the fact that you can't see the fringe pattern in this 0.78 micron cell is because the fringe separation is too small to be resolved by the optical microscope. But independent experiment shows that the pattern quality is also very high in the cell. Okay, so in here already you may notice that the contrast of the pattern is higher for larger pattern period. It is because the inhomogeneous liquid crystal alignment actually relaxes to a uniform state as you move away from the alignment surface by a distance comparable to the pattern period. And therefore, the smaller the pattern period, the less the fraction of the liquid crystal inside the cell possess inhomogeneous alignment and therefore less contrast. To confirm such uniform azimuthal bulk alignment of the liquid crystal, we examine the cell under linearly polarized light with polarization along the y direction. And then we rotate the analyzer. Now for this particular cell that we examine, we find that the cell look the darkest when the analyzer is rotated to 135 degrees. And this verifies that the liquid crystal indeed has a uniform bulk alignment, and in this case is 45 degrees. But in general, the bulk alignment of the liquid crystal can be anywhere between 0 and 90 degrees. The exact value depends on how the UV dosage in the first and the second exposure compares. We have quantified how the azimuthal bulk alignment angle phi bulk varies as a function of the second exposure time tau 2, given that we fix the first exposure time tau 1 and the UV intensity in the first and the second exposure I1 and I2 to be comparable. Listed in here are the experimental parameters we use in doing this measurement for 3 different pattern periods. As you can see here, for all 3 pattern periods, indeed the bulk alignment angle varies from 90 degrees continuously to 0 degrees as we increase the second exposure time. But what surprises us is that the scale of tau 2 decreases rather rapidly with decreasing pattern period. For example, in here, the difference between these 2 values of pattern period is only about 20%. However, the difference between the tau 2 for these 2 patterns is 60%. In fact, because tau 2 decreases so rapidly with decreasing pattern period, when we made this 0.78 micron cell, we actually had to reduce the UV intensity by quite a lot, compare the difference between these 2 numbers, in order to be able to control the photo alignment process. To understand what factors control the rate of photo alignment, we look into the theory developed by Chigrinov and co-workers. So assuming the angle between the UV polarization and the long axis of the acyl dye molecule to be psi, so these authors propose that the probability density distribution of psi, as denoted by this function f, should vary with time according to the Smolotowski equation, which basically describes diffusive rotational motion under a potential. And for photo alignment of acyl dye, it has been proposed that the potential U should be given by a constant multiplied by cosine squared psi, and where this constant is proportional to UV intensity I, among other variables. For problems like this, it is natural to assume the order parameter to be the statistical average of the second order Legendre polynomial, which takes this familiar form here. Given this formulation, if we know the initial condition, we should be able to solve the order parameter as a function of time. So assuming the acyl dye alignment to be random initially, then the solution to this Smolotowski equation is given in here, where the plot in the lower left is the plot of this function. Now you notice that asymptotically, the order parameter approaches a negative number. And the magnitude of this number, according to this equation, is proportional to UV intensity I. Now recall that the order parameter is this function here. So a negative asymptotic value means that the acyl dye molecule tends to rotate to the 90-degree direction at long times. Now we can understand this tendency of the acyl dye rotation from the fact that this is also the direction that would minimize the acyl dye potential. I should also point out that this behavior is consistent with our experimental observation that the acyl dye molecule tends to rotate to 90 degrees with respect to the UV polarization. But of course, this is not a coincidence. The theorists had constructed the acyl dye potential to reproduce just that. Now I should go back to this to discuss this asymptotic behavior. So notice that this order parameter is proportional to the UV intensity. That means as soon as we turn off the UV light, all the parameters should return to 0. But this is not what we observed. We found that once you align the azo die, they tend to hold themselves up to maintain that alignment. So we need to modify the potential in order to take this into account. Now, another notable result I should point out, because we will use that later, is that the initial photoalignment rate is also proportional to the UV intensity. Okay, what is the modification we need to put into the potential? So by construction, this term is added, and this term should be proportional to the order parameter, and it should also depend on the initial alignment direction of the pre-existing azo die alignment. And where this prefactor in this new term that we are adding here is equal to negative 5kTc, where k is Boltzmann's constant. Now, in order to understand the meaning of Tc, we need to look at the solutions to the Smolov-Chomsky equation, incorporating this new potential. And the solutions are plotted in here. In obtaining this solution, it was assumed that the initial azo die alignment was random, and then at time 0, UV was turned on, and it was left on for some time before it was turned off. These solutions shows that when temperature is much below Tc, like in these cases, the azo die alignment that was produced when the UV was turned on persisted even after the UV was turned off. However, when temperature was approached to Tc, the azo die alignment decays to 0. So this shows that the Tc represents the order-disorder transition temperature for azo die alignment. I would like to now modify this potential in order to accommodate our experimental condition. During the second exposure, there is pre-existing alignment in the azo die produced by the first exposure. However, this alignment direction is perpendicular to the preferred alignment direction according to the UV excitation. Now, because in this formulation, the preferred alignment direction is by default 90 degrees, so to be consistent, we should set the size 0 to be 0 in this potential. If you do that, you will find that the potential can be rewritten into this form. Importantly, when the second term is larger than the first term, or in other words, when the molecular field of the azo die is larger than the driving field of the UV excitation, you will find that this potential has a minimum at psi equal to 0. Now remember that the pre-existing azo die alignment is also at psi equal to 0, so there will be no change in the azo die alignment if you have this situation where second term is larger than first term. In relation to our experiment, it means that the intensity of UV during the second exposure has to exceed a minimum value in order for it to be able to overwrite the azo die alignment produced in the first exposure. Okay, so all the results that we have discussed so far about the diffusion model have been confirmed in the experiment. And with this knowledge, I would like to now go back and try to understand the data that we discussed earlier. Recall that we had raised the question concerning why the scale of tau2 decreases rapidly with decreasing pattern period. But if you look more closely at the data, you may discover another interesting question. And that is, the intensity profile produced by the interference pattern actually has regions where the UV intensity is very low. Recall that there is an intensity threshold in order to override the azo die alignment produced by the first exposure. So it is not clear how we can actually reorient the azo die molecule at these regions. So we propose that the mechanism for overriding of azo die alignment involves the movement of the domain wall between perpendicular azo die alignments. The reason why we think that the mechanism should have to do with the domain wall is because at the domain wall, the average order parameter is 0. and therefore there should be no threshold intensity. Now, in the second exposure, the preferred azo-dye alignment is along X, so we would expect the domain wall to move in such a way to expand the region with X alignment, like you see in this animation. And with that, the potential energy of the azo-dye should decrease with time. Assuming conservation of energy, all that energy should go into polarizing the charges inside the azo-dye. So using this idea, one can derive this equation. In here, E squared should be proportional to the UV intensity in the second exposure. And then based on the diffusion model, this should also be the case for the azo-dye potential U and the initial rate of photoalignment. Based on this, we derive that the rate of movement of the domain wall should be proportional to the local UV intensity. By solving this equation, one would arrive at the result that the time scale for photoalignment should be proportional to tangent pi x over p, where p is the period of the pattern period. In order to see whether this result describes the experimental data, we have simulated the liquid crystal configuration on striped alignment patterns like those you see in here as a function of the domain wall position. And then from the result, we extract the bulk azimuthal alignment angle, phi sub bulk. And I am going to overlay the simulation result on top of these data. We find that by properly scaling this quantity, tangent pi x over p, we can make the simulation overlap exactly with the data. So this confirms that indeed tau 2 is proportional to tangent pi x over p as predicted by our domain wall model. In the remaining time, I would like to show you how we use the photopatterned azo-dye films to make liquid crystal phase diffraction grating. One application is in the optical projection system that was proposed by Chen and colleagues in 1995. In their design, if individual LC pixels are effectively diffraction gratings that can be addressed electrically, then one should be able to control when to allow light coming from individual pixels to be transmitted through the screen. Now, to make the diffraction grating as such, consider the following liquid crystal cell, in which the bottom plate is made of the photoaligned azo-dye film in the way that we discussed, and the top plate is made of alignment layers that will align liquid crystal perpendicular to the alignment surface. With this, when light comes in, whether it is polarized in the x direction or in the y direction, it will see the liquid crystal to be an inhomogeneous medium with dielectric property that alternates between parallel strip domains in which the refractive index is a constant, equal to the ordinary refractive index of the liquid crystal, or in domains where it sees the refractive index to be an effective value that depends on the local liquid crystal critical angle theta according to this equation. So with this, there should be an inherent phase difference between light coming from adjacent domains that should depend on the integration of n effective minus NO along the z direction as given in this equation. Now, because n effective is determined by the liquid crystal critical angle, that means we should be able to control the phase difference by applying a voltage across the liquid crystal cell. In particular, suppose we apply a voltage that makes this phase difference equal to pi. With that, the diffraction pattern produced by this grating should be shifted laterally by a half period with respect to that we would expect from an ordinary diffraction grating. In other words, voltage will convert a diffraction peak into a diffraction minimum and vice versa. By using this concept, we have made liquid crystal diffraction pattern grating using our laser dye fans. We use this setup to test the diffraction grating. We put the detector at where the first order minimum should be for an ordinary diffraction grating, and then we measure the detector signal as a function of applied voltage across the diffraction grating. And the data is shown in here. Starting from very large applied voltage, where the phase difference that we discussed should be very small, and therefore the signal is also very small. But as we decrease the applied voltage, the phase difference increases. And until it is equal to pi, we obtain a peak, as we would expect. We find this behavior to be quite independent of whether the incident light is polarized along X or along Y. And that means our grating can be used for unpolarized light. Now, I should point out that this capability represents a major advantage over devices that require polarized light for operation, such as the 90-degree twist pneumatic liquid crystal cell that we discussed in the introduction. It is because the use of a polarizer often means that a half of the energy of the light source is wasted, and that means low energy efficiency. And with that, I should conclude my talk. We have discussed how inhomogeneous pattern surfaces can be used to control the alignment of liquid crystal. And in particular, we demonstrate that we can use these surfaces to achieve large liquid crystal reticle angle. We also show how to make inhomogeneous surface patterns on an laser dye film by exposing the film to an optical interference twice. But in this process, we discovered that the scale for the second exposure time decreases rapidly with decreasing pattern period. And by using the diffusion model as the basis, we propose a model involving the movement of the main wall between perpendicular laser dye alignment domains to explain this observation. And finally, we demonstrate how to use the patterned laser dye films to make polarization independent phase diffraction gratings, which are desirable for energy efficiency. Let me spend some time acknowledging the people and the funding agency for support of this work. Shen-Ming Liu was a postdoc in physics HKUST. He did most of the photo-alignment work. He is now a professor in Shanghai Jiao Tong University in China. Ophelia Tsui was a graduate student in also physics HKUST. He did most of the work involving the AFM pattern surfaces. He is now a research scientist in Hong Kong Polytechnic University. Peng Shen is a theorist in physics HKUST. He helped us with the computer simulation work. Hoising Kwok and Viktor Chiganov are in the EEE department, and they help us with the device aspect of the project. Chenghua Liu is a professor in Shanghai Jiao Tong University. He helped us with the liquid crystal diffraction grating work. I should also thank Wing-Yin Tam and C.T. Chen. They had kindly allowed us to use their helium-cadmium neon laser. And this work was supported by Research Grant Council of Hong Kong through 2 projects. And I would also like to thank Nippon Inc. and Chemicals in Japan for providing us the SD1 material. Thank you very much for your attention.
Thank you very much. Are there questions?
What is your Ezos film? How it is made, and have you tried to characterize the alignment and then relaxation phenomena?
Right. So this film was essentially made by spin coating, and then we annealed the film inside a vacuum oven for some time at some temperature. The details for film fabrication, I will refer you to a previous publication by Chipinov and co-workers. We can discuss in private for where to look into that paper. And in terms of the characterization of the alignment and the relaxation, also can be found in that paper.
Other questions?
I have a similar question. One of the concerns that we have when we try to model orientational photo bleaching, right, the reorientation of the azo on some substrate is, well, how much of it is actually standing up and going out of the plane of the substrate? Is that something you have thought about? I mean, because ultimately that's probably where it would like to be if all other things were equal.
No, we have not thought about that because our goal for this project is to produce inhomogeneous in-plane alignment. No, so basically our usage of the azo guide is like an engineer. We just make use of what it behaves and then to achieve what we try to achieve. No, we haven't thought about that.
Other questions? I was going to ask about the longevity of the effect, if there is some kind of degradation of the performance independent of this residual alignment. But in addition to that, if it were continued to recycle, if it were continuing to perform the same way, or if it degraded with time over a longer period of time.
Right. Now, in terms of longevity, we find that these pattern surfaces still perform over weeks. Now, we haven't on purpose examined whether they still perform beyond that time. So I cannot answer your question, how long it lasts. I can only say at least several weeks. Now, we do find that overwriting of the alignment on top of pre-existing alignment, the quality degrades. The more number of times you do it, the worse it takes. That's why we find that we have to use the interference method the way we did to achieve high quality patterning. Instead of, we have tried, for example, first uniformly aligning the liquid crystal by UV beam, and then we illuminate it with a patterned interference pattern, and that doesn't work as well as the way we do it in what I just described.
Thank you. Other questions? Okay, then we'll move on to the next phase of the session, which are two contributed talks. Both of these talks are from members of the Liquid Crystal Research Center here in Colorado.